Alrighty, guys, can you hear me? Can anybody hear me? Okay. Before we get started, are there any questions? Any questions, or you just want to get started on the lecture? Okay, then we'll get started on the lecture. There's a question here. Do we have a week off? There will be changes around Thanksgiving, yeah. Let's see. I believe that Wednesday before Thanksgiving, there will be no TA session. There'll be a lecture. There'll be a lecture on that Tuesday before, and then there will not be any TA session, and there'll be no office hours, and there'll be no homework. Right, that's around Thanksgiving. I updated the, so maybe I should write this. So so there's an updated syllabus. And I should also say that the final exams are being scheduled. So contact me for a slot. And so there's no homework. Problem session during the week of Thanksgiving. I forget how it is. They always change. I just got an email about it this morning. They always change the designations around. So let's see. So Wednesday, November 25th, becomes a Friday. So we also there's going to be no office hours. On Wednesday. No, not Wednesday. This is Thursday, November 26th, and then Friday, 27th. So we will have a lecture. Tuesday, November 24th. Are there other questions or comments? Well, if not, we are, so we've today we're going to be doing fixed income modeling. Right, and this is section 6 or chapter 6 in our textbook. Okay, so in fixed income, uses stochastic interest rates. So there is a stochastic process now that's denoted by Rn. So these are stochastics, whereas before In would just be this interest at this constant. So now it's a stochastic process. And so examples, there are some popular choices. There's something called a Ho and Lee. Ho and Lee model. This one takes Rn to be a constant, An plus Bn, another constant, times, and then the number of heads. Remember this notation here, this is the number of heads in first n tosses. An and Bn are constants. And they could depend on n. So this is just a side comment. So the notation is Rn. So when you see the subscript here, the subscript it indicates a stochastic process. So this indicates stochasticity. Whereas if I write something like this with the n inside a bracket, this is so this is n is a subscript, and here if n is inside parentheses, this is a non-random quantity. So when you see stuff like this, the number of heads in the first n tosses, this is a random quantity, whereas An and Bn are just constants that could vary with n. So that's the Ho and Lee model. The other one that's popular. The other one that's popular is the Black-Derman and Toy. So the Black-Derman and Toy model is very similar to the one we have up here. You write this as Rn And again, you have an, but then instead of a plus, you put a multiplicative sign, and then you raise the b to the number of heads. So this is just two specific examples of a stochastic process for Rn. There are many others, and so we shall see many other examples, including in a TA session. Okay, so we have focuses on this stochastic process Rn, and okay, so what changes? Well, the money market account. The money market account has dynamics. Well, how did we usually write it? We would say it would be S. So this was before. We would have Sn would be like the previous one times 1 plus R. Right, so this would be Sn minus 1 plus R times Sn minus 1. This was before. So we could write this here as delta Sn would be R Sn minus 1. This was before, so now this was with a constant. So now with the stochastic one, it's going to change a little bit. And the way that it's going to change is Sn is going to be Sn minus 1 times 1 plus, and then you have this R n minus 1. And we can write in the changes in the money market account. We've been putting a 0 up here, so let me put a 0 up here again. My camera is blurry. Dawn is saying my camera is blurry, so on my end it looks fine. Is it blurry on everybody's end? Is it blurry on everybody's end, or is it clear on somebody's end? Bashir says it's good. Okay. Dawn, can you try to refresh it and see how it goes? We were putting in these zeros. Yeah, normally when we do the money market account, we have a 0 up there. Okay, Dawn is back online. Great. I said this is now with stochastic. With the stochastic Rn. So what we do is we change this R to being Rn minus 1. Please note that this is not a typo. This is not n. And then we can do the same rewrite as what we had up there. We write this as delta Sn 0. This is equal to, well, it would be Rn minus 1 times Sn minus 1, 0. So what happens is that at time at time n minus 1, so we're sitting here at time n minus 1, and we're worrying about, we're going to have a stochastic interest rate environment. At time n minus 1, we know Rn minus 1 which is the rate over n minus 1 to n. So we know here what the interest rate at time n minus 1, we know what it's going to be over that interval. But at time n minus 2, we don't know n minus 1. And so when we're sitting here, if this is n minus 2, I don't know what the interest rate is going to be over that period from n minus 1 to n minus 2. So we don't know. We don't know the rate over n minus 1 to n. So we only know the rate over the next period. We don't know the rate that works over the next 2 periods. Right, so time n minus 2, we'll know what this rate is going to be like, but we don't know what this one is. So we have stochastic interest rates. But over the next period, we know what they are. So just keep track of the indices. This here has to be n minus 1. You cannot put an n there. So how do we get the traded securities? The traded securities are now zero coupon bonds. So we always model zero coupon bonds in fixed income. So we always have these zero coupon bonds, right? So they're called CCB, zero coupon bonds. And so what is that? Well, we're going to have a maturity or expiry. So this is going to be M. And the reason it's called fixed income is because we know what this payment is going to be. It's going to be $1. So a zero coupon bond expires at time M, and it pays out $1. And now we're looking at an earlier time point, let's call it N. And so what we have to do is we have to move this $1 here over to time N. Right, so the price, the zero coupon bond price at N, which is less than M, this is denoted BNM. And of course, this is positive. Are we good so far? So if I'm interested in the value of $1 at a future time point, okay, if I want to know what that $1 is at an earlier time point, then that value is going to be denoted by BNM. So how do we model these? So how to model well, we want one property we want is if I put in here BMM, what should I get? What should I get for BMM? I should get 1, that's correct. And the other thing that I want is I want no arbitrage. I want no arbitrage. So I want a measure that's denoted by p tilde such that B divided by the money market account, this object here, indexed by n, is a p tilde martingale. So how should we accomplish all that? So I need this and I need that. How should I write down my zero coupon bonds? We don't have a stock here, right? Because a priori, the only thing that we have going for us, the only traded security that is being given is the money market account. Like, and now, so we want to create these zero coupon bonds. Like, there's no stock, at least at this point in our analysis. There's a money market account, and then the zero coupon bonds, and we're trying to figure out how we should write down the value of a zero coupon bond at an earlier time, such that I'm consistent with no arbitrage, and such that when I run the process forward to the end, I'm going to get this $1 that sits up here. The question is, how should I do this? And so what we do is you fix a probability measure. Probability measure denoted by p tilde. So for example, we would have this p tilde be like half for heads and q tilde for tails. Something we've had a lot of times. So we fix a probability measure, and then we simply just define the zero coupon bond. So this is a definition. This is not we define this stochastic process by whatever I'm going to write here. This is going to be this E tilde, and then upstairs I'll put SN0, downstairs I'll put SM0, and then I'll condition on FN. So is this a good definition? Does it obey the two properties? So let's check that star and double star hold. Well, the first one is the easiest one, because if I look at B, what was it, MM, BMM, so I'll take M and N to be the same. I'll get E tilde, and I'll have SM0 over SM0 given FM. And that is exactly 1. So that one works. This was star. So let's do double star. I'm interested in B and M divided by, see what was we had here. We need to discount by the bank account, SN0. This is SN0. Okay, so what do we get here? This is 1 over Sn0 times E tilde. We just plug in the definition up here. Sn0 is M0 given Fn. And then I'll use that this quantity here, the money market account's value at time n is going to be Fn measurable. This thing can travel inside here, can go inside, and it'll cancel out what I have upstairs. And we have seen this before, that this here is a Levy martingale. Under that measure, I'm conditioning under. Do we all remember these Levy martingales? Maybe we should just refresh them. So recall that for a random variable with a finite expectation, Mn being the conditional expectation, it's this property here I'm using, that I take a random variable, it has to be integrable, then the conditional expectation is a martingale, and to prove it, it's not bad. You look at Mn plus 1 given Fn, plug in the definition, and then I use that I have Fn plus 1 and Fn next to each other. The smallest one wins. And that's exactly my image. And so when I take a random variable, it's important here that the random variable A, there's no index, this time index n here is nowhere to be found around A. Like, this doesn't work. It does not work if A depends on n. So you cannot have that. There can be no n around A. It's not true in general that E tilde of An given Fn. This is in general not a P tilde martingale. So it's important for this argument that we don't have any n dependence upon the A. So let's just double check here. Our A here is 1 over Sm0. So there's no n dependence on A here, so that's good. So that's my so that's the property I needed. And when I discount, I get a martingale. Then I'll be free of arbitrage. And, the last time we concluded by we ended up having a discussion about what do these zero coupon bond prices, what do they look like for specific N and M's? So maybe we should just recall that one more time. So some special cases, if I take, if I look at B01 1. So try to work out what this conditional expectation is when n is equal to 0 and m is equal to 1. Well, I'll get e tilde, and then n would be 0, so I'll have a s0, 0 upstairs, and then I'll have s0, 1 downstairs. Condition on f0. So what would that be? Well, it'll be e tilde s0, 0. This is always taken to be 1. And then downstairs, the money market account value at time 1. Well, let's go back and have a look. So here we have a 1. So this is going to be 0. I'll get 1 plus R0. Okay, so I'll get 1 plus R0 conditioned on F0. R0 is 0 measurable, so this will be 1 over 1 plus R0. So that was the first one. So if I go out to 2, if I look at B02, and then what would happen is I will keep the 0 up here, but I have to put a 2 down here. So I will look at E tilde. So again, S0, 0 over S0, but now a 2 given F0. Okay, so let me write out what that is. Let's do the 1 upstairs. And then downstairs, it'll be 1 plus R0. That was my S1 times 1 plus R1 given F0. So now I have an R1 here and I have an F0. So this thing here is not, R1 is not going to be F0 measurable. The best that I can do is write this as, I can take the first part outside if I want to, times 1 over 1 plus R0. So I want you to just note that this here is not the same if I were to write down 1 over S02 here. That would become, that would be 1 over 1 plus R0 times 1 plus R1. And we should note here that this is F2 measurable. This is actually F1 measurable. This is F1 measurable because you have a 1 here. Whereas this quantity up here, this thing here is F0 measurable. Okay, so we don't have, so we cannot have that the 0 coupon bonds are just equal to 1 over the money market account. So we cannot have this. Any questions up to this point? So what we're using here is, this here is our starting point for how we're going to define 0 coupon bonds. So I had a couple of problems prepared. let's have a look at some of the sample problems. Some of the sample problems. Problem number 10. Right, so I'm hoping we can all see my problem number 10 here. There's an interest rate model. There are, how many? 1, 2, 3. There are 4 zero coupon bonds, so we have to compute. And let's see what we get of these 4 guys. Okay, so this is problem number 10. I want to switch back to my document camera. This is problem number 10. We're looking at an interest rate model where Rn plus 1, this formula for it is 1 plus Rn times these epsilons minus 1. So we have our epsilons, they are IIDs. Yeah, IID. You have the coin flips, so you go up to 2, and you go down to 1, and you have probabilities 1/4 for going up and 3/4 for going down. So those are my size. The interest rate model looks like this. The initial point is taken to be 1/4. And so then the goal is to compute a bunch of interest rates, so a bunch of zero coupon bonds. So compute the zero coupon bonds. B, M, M. Well, that's the easiest one. This is equal to 1. That's how it always is. And let's see what we also have to compute. We have to go 1 back, so we have to compute B, M, minus 1, and M. But then we use the formula. We use the formula. Here we will have this would now be n is equal to m minus 1. So we will have S0 m minus 1 up here. We'll have Sm down here. E tilde Sm minus 1 divided by Sm given Fm minus 1. Right, this here is the price. So again, remember, this is the current time. And this one here, this is expiry. As a current time, we always condition on current time. Expiry is downstairs, current time is upstairs. So we plug in what we have. What's our model? Well, the model says the zero coupon bond dynamics are that here we have Sm is equal to Sm minus 1 times 1 plus, and then you have your R, M minus 1. And then upstairs you have Sm minus 1. So we're doing nothing else. Doing nothing else than, where is this page? here. We do nothing else than just using the definition of the money market account. So if I'm interested in what the value is at time M, I go back one here and I go back one here. So that's all I've done down here. Just use the definition of what SM0 was. And now we can see the cancel, and I can also see that the remaining component is already measurable. So this here just becomes 1 over 1 plus R M minus 1. Questions so far? We good? Let's go back one more. So we'll look at page 8. Go back one more. So we go back to BM minus 2. So again, what changes is the indices change. M stays the same downstairs, but instead of M minus 1, I'll have M minus 2, so I have an M minus 2 up here. And then here I have it as M given, and then there's always current timing condition on. So what will I have here? Well, I'll do the same as before. I'll replace SM by SM minus 1, and then I'll replace SM minus 1 in terms of, write SM minus 1 in terms of SM minus 2. So downstairs I'll have SM minus 2 times 1 plus R M minus 2 times 1 plus R M minus 1 given Fm minus 2. And again, they will cancel out. And again, there'll be something that is measurable, and then we have this one. Now this one here is not going to be measurable anymore. So this here becomes 1 over 1 plus R n minus 2. And then we have the expectation of 1 over 1 plus R n minus 1 given Fm minus 2. And so how do we work this out? Well, now is the time to use how the interest rates are connected over time. And so we use the formula here. I'll use the 1, I'll move the 1 to the other side. Right, I'll move this 1 to the other side. Okay, so I can go 1 back in time. I can go from 1 plus Rn plus 1. I can go back to 1 plus n, but I have to multiply up this independent coin flip random variable. So I can do that. So this becomes 1 over 1 plus Rm minus 2 squared. And then expectation of 1, and this is on the tilde measure, over 1 over epsilon m minus 1 this one was independent of the previous coin flips, so we just get the unconditional one. And we can work out what this expectation here is. This would be P tilde times, this was U and D, so 1 over U plus Q tilde 1 over D. And P tilde was it, a quarter times U was a half plus, and then Q tilde was 3/4 and D was 1. What does it come out to? This is 1 over 8. This is so 7 over 8. And then the last one that we're being asked to compute is, we go one more back to m minus 3. So we can see for the first two questions, there was no need to know how the interest rates are related to each other over time. This is always 1, and here you know what the interest rate is over the next period. You don't need to know anything about how the model. Here, this is the first time we use that we actually know we need to compute a conditional expectation. And then of course, sanity check, right? This here has to be, this is the price at time m minus 2. So whatever we get out here, this quantity has to be fm minus 2 measurable, right? And it is. Let's compute the last one. This would be b of m minus 3 and m. So we can almost see what it's going to end up being. Well, let's write it out. It'll be E tilde. Upstairs you would have Sm minus 3, 0 divided by Sm, 0 times given Fm minus 3. And then we'll work out what it is. This will be E tilde. And then we'll plug in what this one here is. So this would be Sm minus 3, 0 times a bunch of things. 1 plus R m minus 3, 1 plus R m minus 2, 1 plus R m minus 1, given F m minus 3. And so what do we get this time? Well, again, you will cancel out, and this one here will be measurable. You will get E tilde 1 over 1 plus R m minus 2, 1 over 1 plus R m minus 1, given F m minus 3, 1 over 1 plus R m minus 3. And so comes the time when we need to use the recursive formula for how the interest rates are linked over time. And if we plug that in here, I can bring this one here back 1. This quantity here is 1 divided by 1 plus, and then I go back 1 by multiplying onto this epsilon n minus 1. So that's the same one. That was the same one as what we had up here. Okay, so now I can combine the two. I'm going to get a square. Combine these two and I'll get a square. So let me write that as 1/1 plus Rm minus 2 with a square 1/epsilon m minus 1 given Fm minus 3. So what about this one? I'll try to do the same. I'll roll it back one more. I can write this here as 1/1 plus Rm minus 3. And the price I'm paying is an epsilon m minus 2. Right, and then everything is squared times 1/epsilon m minus 1. And so now I'm in better shape because this one here is now measurable. These two guys here are independent, and they're also independent of Fm minus 3. So if I combine all these things, I will get that this here is equal to 1/1 plus Rm minus 3 squared times the expectation of 1/epsilon m minus 2 squared times the expectation of 1/epsilon m minus 1. And we already figured out what this one here was from before. This was 7 divided by 8. That was this number we found before. And so now we just have to compute what this one here is. So it will be p tilde times 1/u squared plus, so this is this quantity, p tilde over 1/u squared times q tilde plus q tilde times 1/d squared. P tilde was a quarter, u was 2, so this is 1/4. Q tilde was 3/4, d was 1. So this is 16. This is 12. This is 13/16. So b m minus 3m, this is equal to 1/1 plus m minus 3 squared times 13 divided by 16 times 7 divided by 8. And just a sanity check, this here really is, this is Fm minus 3 measurable. The random variable is this one, these are just constants. Yep, are we good so far? You guys are very quiet today. Are we good so far? Dawn says yes, that's awesome. What about the rest of you? This here was an old exam question. I think I actually handed it out last year. So last year about this time, the students do get a question like this one in a written exam. I had one more in mind before we move on to something else. Some of you have asked if I could do more examples, so I'm trying to do a few more examples here in class. Let's try to do one more question. So I do, this is problem number 15. Let me just bring it up so you guys can see it. Share. So then the last one that I wanted to do is this this question here. So again, we have zero coupon bond prices. And then there's a relationship like this one. Can I just multiply previous zero coupon bond prices and get the current one? And then there are questions about measurability and so on. So let's see if we can answer this problem here. See if we can get this one here to work. So do we always have, so this is the first one. Do we have, if I look at the zero coupon bond going from, so here I have n plus 1, I have n plus 2, I have n. So I'm interested in a zero coupon bond that goes from n to n plus 2. Can I always write this as n, n plus 1, n plus 1, n plus 2? What do you guys think? Well, to get started on something like this, you should look for measurability. So this quantity here is, what kind of measurability? Oh, it's not showing the right thing. Sorry. Thanks, Meow. Do we have that? Do we have that the zero coupon bond at time n can be written as this product here? So you go. The question is, can I go from n to n plus 2? Simply by going from n to n plus 1 times the one that goes from n plus 1 to n plus 2. Do I have such a structure? So we're interested in moving this thing over here. And the question is, can I do something like this? Well, this one here is, Rocher is saying that this here is, there's something with measurability, and that's correct. So the answer is no. Because this one here is Fn measurable. This one here is Fn measurable. But this one here, this is Fn plus 1 measurable. So we have a problem because when I multiply these two together, I'm going to get something that is Fn plus 1 measurable. And I need it to be Fn measurable. So that's a no. Can't have that in general. Second bit is, if I look at B and M, so is B and M Fm minus 1 measurable? What do you think? Which is yes. right? So let's check this. Test it out. So for n less than or equal to n minus 1, if n is less than or equal to fn minus 1, it works. Because then you want to have that, you always know that this is fn measurable, right? And you will have, because fn is going to be inside fn plus 1. So that fn minus 1, sorry, these are minuses. So the only problem that could be problematic is the last one, when you have n is equal to m. But then we're safe, because m is equal to 1, and this is a constant, and this is also fm minus 1 measurable. So that one works. The third one is, if I take, do we have that B0m is equal to 1 over SM0? Is the zero coupon bond just the inverse of the money market account? What do you guys say? Yeah, it says no. I agree. This is a no. So here we're going to have that this is F0 measurable. And in this quantity here, this is going to be Fm minus 1 measurable. So you don't line up. And so Hoshi is right. This is one step. This only works for one step. It doesn't work in general. And the final fourth question is, do we have that B0M is equal to the conditional expectation of 1 over SM0? So now we don't have this problem anymore. This is F0 measurable, and this thing here is also going to be F0 measurable. And this one here is a yes. Okay, so these are some old exam problems that have been given out in the past, and I'm hoping you're getting some sense of what a zero coupon bond is and how you get these things created from the money market account. Are there any questions on what we've been doing here? Okay, then let's try to move on a little bit. There are some concepts that are related to these zero coupon bonds that people use. So they are related concepts. So I don't use them very much. So I don't use them. I don't use them in class, but many other people do. But many other resources do. So you should know that they exist and what they are. There's something called a discount factor. It's also sometimes called a discount process. It's denoted by dn and our textbook. So for example, our textbook use that. And it's nothing else than just 1 over the money market account. Right, so if you want, you can write this out as 1 over 1 plus R0, 1 over 1 plus R1, times 1 over 1 plus R n minus 1. N minus 1 here. Right, so you can see here that this is f n minus 1 measurable. So that's my dn. I prefer to use, I don't see the need to introduce dn given that we already have Sn0. But some people use this, in particular our textbook likes this dn. There's also something called a yield. The yield ym, this is a constant. And then the way that you write the yield is by saying that the zero coupon bond working over m periods, you write this as 1 over 1 plus ym to the power m. So you can think about a yield. This is like a constant interest rate. Because this is exactly what the zero coupon bonds would be had the interest rate been constant. So there are two related concepts here, yields and these discount factors. Okay, so another thing that we have talked about a bit is that this recall. So for Sn stock price, we have that Sn divided by the money market account. This is a P tilde martingale. Okay. And we saw that because of this, if I look at the wealth divided by the money market account, this is again a P tilde martingale, right? Where if I looked at the wealth would be, it would be defined to be just the number of shares of the money market account times the money market account plus the number of shares of stock times the stock price. And we will also have the self-financing, property that would say that you could write this xn here as whatever you had before trading at time n, times the prices at time n. And so if you wanted to provide this Sn here, you could write that as Sn minus 1 and then times 1 plus the interest rate. And so now in our case, this is Rn minus 1. And then you could write this quantity here. This would be xn minus 1 minus delta n minus 1 Sn minus 1. So that will be your x in that will be your x in the case you had a traded stock. So now now it's going to be a little bit different. It'll be very similar, but the difference is you're going to have more here. Right? So we could combine all these expressions to be 1 plus Rn minus 1 times, what would it be? Well, you have your x, okay, so you have your xn minus 1, and then you'll have a plus, and then you'll have your delta n minus 1, Sn minus Sn minus 1. So this is when you had the stock. So now it's going to be more general, right? So for us, so we now have, so we can invest in fixed income. So in fixed income, there's no stock, but you have your zero coupon bonds. You have B and M. So you have M zero coupon bonds. You have one that expire. I mean, you have as many as you have expiration points. So you have zero coupon bonds with expiry m equal to 1, m equal to 2, m equal to 3, and so on. M equal to whatever general number you want. So you don't have a stock. So this term here, that is not there because we don't have a stock price, but we have zero coupon bonds. So this term here has to be altered. So you have the position of a zero coupon bond times the difference in the zero coupon bond value. Okay, so this term here, so this means, so we replace delta n minus 1 times Sn minus Sn minus 1 with, and then we have to write delta n minus 1 and then m times b, and then here you would have n m minus Bn minus 1 M. And then how many would you have? Well, you'll be summing up over however many you have. So what we have here, this is the holding. This is the number of zero coupon bonds with expiry M at time n minus 1. So again, we have that B and M divided by S and 0. This is a P tilde martingale. Right? That was the starting point we started out with. Let's see if I can find the slide again. Starting point. So it's the starting point that we wanted to take the zero coupon bond, discounted by the money market account, and get a P tilde martingale. So that's exactly what we had for the stock. And because of this, the discounted wealth would again become a martingale. Likewise, what you have here, and this is going to imply that your new wealth divided by Sn0 is again a P tilde martingale. But now you're replacing this term here with this big sum. What else? There was one more thing I wanted to mention. So related concepts. So we have discount factor, yield, wealth process. We should also say coupon bonds. So coupon bonds. So imagine that we are interested in pricing payments that come in at time. There'll be a payment coming in at time M, M plus 1, M plus 2, M plus 3, and say that these payments that are coming in will just be CM, maybe there's a smaller one here, CM plus 1, maybe there's a big one here, CM plus 2, and CM plus 3. Say that, and these are all constants. So you have a coupon bond that pays out non-random quantities. If I am to price this coupon bond here at time n, what I'll need to do is I'll need to move all these payments from their respective times back to time n. Right, so I have these deterministic, these non-random payments coming in at later times. How do I move them back? Well, the price at time n, well, how do we move a payment from time m to time n, given that it's not random? Well, you take the payment, and then you multiply onto the zero coupon bond, and then you sum. So this here works when C of m is non-random. In other words, if I know how to price zero coupon bonds, it's not a big leap to figure out how to price coupon paying bonds. Okay, I think this this might be a good place for us to take a little break. Are there any questions before we take a little break? Are there any questions or comments? If not, let's take a little break, switch over to the other Zoom link, and then I'll see you in 10 minutes or so.